one, what it is that's expected of us, and two, where we're going with this and how this all fits together. Because I don't want any confusion. And can I ask you guys a favor, please? At any given point, if there's something that you're not understanding, raise your hand, ask a question, say, hey, Chris, how about this? Or what about this? Or I'm not getting this. Can you explain this a little bit more? I would appreciate that, right? I'm trying to teach this. I don't think there's any such thing as a dumb question. I'm not going to insult you. I'm not going to make you feel like you're dumb. No, I'm going to empower you with information to teach you. So please, at any given point, just ask. Okay, we're just going to jump right into the PowerPoint slide, the presentation. I figure at this point, if you don't know the difference between a population and a sample, it's probably not going to happen. Okay.
A small question.
Sure.
So business 211, what is the difference between this and business 211?
Between the two different classes?
Yeah.
So this one, we're looking at statistics. So we're looking at how to look at data, compare data, and based off of seeing different or patterns in the data, seeing if there's some differences, if there's some trends, if there's something going on in the data. So we can analyze data, we can analyze information. 311 shows you how to make a database and collect and organize that data. So one of them supposedly is to get you a database, show you how to organize that database, show you how to store the data and how to retrieve it. What I show you is how to analyze it.
Okay.
So what I'm saying is that the two are connected, or they're supposed to be connected, but my part comes on how do you analyze it and what does the data mean. That's the difference. Okay? So now what we're going to look at is we started looking at yesterday, we started looking at the assumptions. So what I want to say again is that regression, what we're looking at is slopes. And we're looking at something that has a constant slope to it. And as one thing increases, the other one increases. We have an independent and dependent variable. And we can test things to see, or we can actually start to do forecasting based off of these constant slopes. Okay? Now, after we're able to come up with some type of analysis and some type of forecast, what we need to do is to make sure that our forecast is, one, reliable and valid. And so in order to make sure that whatever we're coming out with is actually real, what we have is some things that are called assumptions. And those assumptions allow us to make sure that whatever we're testing, whatever information we're coming out with is actually real. Can I ask you guys if we can actually put on our cameras? I know that there's some people that don't have theirs on, and I really need to see you, to see what's going on with you. So if we could, please. I know, Melissa, you don't like turn on the cam. It's Caitlin as well, and some of the other ones, but please turn on your cameras.
Sorry, I'm on a desktop. I don't have a webcam.
Okay. But whoever does have a camera, Brooke, you know, if you do have one, can we turn that on, please? I want to be able to see, just to be able to see your reactions of what's taking place with you, please. Otherwise, when you get stuck, and this is the part that it's going to happen, we're going to have problems with that. Kelly, are you there?
Yes.
Okay, can you turn on that desk cam?
Oh, I don't have a webcam.
Or you don't have a webcam. Okay, how about you, Caitlin?
I'm on a desktop today, but usually I do have a camera. It's
Okay.
just that I don't have one.
Okay. Well, let's please, if we could, let's move forward with that. Otherwise, like I said, when you do get stuck, it's going to be hard to see everybody's face to see where they're at, because I do look at it as a metric. Okay, so now let's look at our assumptions. Once we have come out with some type of forecast, and we're able to say, hey, I believe this is taking place. I believe if you have a house that is 2,000 square feet, this is how much it should be. Looking at some type of stock, this is where that stock should be tomorrow. If if this happens to the market, this is going to happen to that stock. We can actually start to forecast stuff out. And once we're able to forecast stuff out, put together something called a budget, create something like cash flow statements of money coming in and money going out. And we want to create a budget, and we're trying to get it past the council, right? We're trying to get it past the people that have oversight on us. We're a publicly traded company, and these numbers have to be right. We need to make sure that they're right. We need to make sure that all these numbers are accurate. Because let me say this. I want to drill this in your head. You become a manager, you become a CEO, and you have people that work for you. And these people that are working for you, come Friday, they're working till late. Their kid's out playing football, and they're not watching. Their daughter and son are in these Christmas plays or whatever it is, and they don't make those plays. You know why? Because they're working. And they're working their butt off for you and for the company. And you make some mistake, and you fire them. You lay them off. And it has nothing to do with them. After all those years of all those sacrifices that they've done working for this company, and you, just because you make a mistake and you have this pride, I don't want to admit to anything, or I don't want to check to make sure that it's accurate, you lay them off and fire them. That is wrong. That is wrong. And so we don't do that. We don't make careless mistakes like that. What we need to do is to make sure whatever we're doing is accurate. Not only for us, because we don't have something here to prove for us. We're in here running this company for not just us, but other people out there as well. And we can make sure that everybody's well-being is taken care of. So we want to make sure that whatever we're running is accurate, or at least as accurate as it can be. So after we're done running this regression, we have these assumptions that we check. And what we like to call them is whenever you run regression, you need to draw the line. Our assumptions are linearity, independence, normality, and equivariances. Okay. Now, linearity, we need to make sure that if we are making this claim that as square feet increases, the price of the house increases, and we have a slope, we need to make sure that it's linear. We do not want to have any curvilinear patterns happening here, right? We do not want to have any curvilinear patterns. Because if it's curvilinear, that means it's not linear, and we can't use this. Okay? So we're going to run our assumptions, and we're going to have something known as residuals. And we're going to look at our residuals, and what we don't want to see is a curvilinear pattern in there. If we see a smile or a frown, that means that it's curvilinear, and we can't use whatever that variable is. What we want to see is some randomness in our residuals. We're also going to look at our independence. And so what this checks is to make sure that we actually have a slope. What our independence checks is we have something called a standard error. A standard error. And what this checks is the accuracy of the standard error. Right? And so we're going to look at either a pattern or our Durbin-Watson. And our Durbin-Watson has to be greater than 1.3. If it's greater than 1.3, it means that our standard error is okay. So far, so good. Now, the next thing that we look at is our normality. We've used this normality in t-test and ANOVA. And so we're looking at our skewness and kurtosis. And we're trying to check out our accuracy of the p-value. Right? You can also look at a normal probability plot, box and whisker, whatever. We just want to make sure that our data is normal, that it has a normal shape. Our equivariances tells us that our error or our standard deviation is constant. It's not increasing as time goes on. So if we have a slope here, we want to make sure that our equivariances, that our standard deviation stays the same over time. If it starts to increase and decrease over time, it's not constant. And so we want to make sure that our variability is constant over time. So what we don't want to see is that wedge-shaped pattern in our residuals. So again, if we see a smile or a frown, it's not linear, you can't use that variable. If our Durbin-Watson is not above 1.3, what it tells us is our standard error is no good. If our skewness and kurtosis is not between -1 to 1, it tells us that our p-value is not accurate. And also, it would tell us that our confidence intervals and a lot of other things aren't good either. Now, if we see a wedge-shaped pattern in our residuals, it's telling us that if anything that differs from that line is called an error. It's telling us that future errors are based on past errors, which means that it is building. The errors are building upon themselves, and it's getting worse and worse and worse over time. Those are kind of our assumptions of our regression. And we want to make sure that our errors are kind of constant, right? And so when we're looking at our linearity, we don't want to see a pattern like that. We don't want to see a pattern like that, right? So that either a smile or a frown, what we want to see is this randomness. The one at the bottom that says linear, we want to see randomness in there. For our independence, now if we're looking at data that's taken over time, first, second, third quarter data, couple weeks, right? So something that's over time, we probably want to look at our Durbin-Watson, but if we're looking at, just data that's maybe it's observed like now, right? But there are a couple different instances too as well. But so we can either look at our Durbin-Watson, and our Durbin-Watson looks at autocorrelation, or we can look at this. And we can also look at our residuals to see if we see a snake-like pattern. If we see a pattern like this, a pattern like that, we have a problem. What we really want to see in our residuals always is this randomness. Okay? Randomness. So for our normality, we can look at a normal probability plot. I like skewness and kurtosis, right? I like skewness and kurtosis. But we can look at a normal probability plot as well, or we can look at box and whiskers. So in our equal variances, we don't want to see this wedge-shaped pattern. What we want to see again is randomness. If we see patterns in any of the data, what it's telling us, let me just take a step back and talk about a residual, okay? Just to take a step back so you can kind of get a sense of what it is. So, Elisa, do you cook?
I like baking more, but sure.
Okay. Baking. Wait a minute. Just kidding. Right. So we're just going to say Elisa cooks. And imagine Elisa's going to throw a party. We're all going to go to the party, and she's going to make like curry. So over noodles or rice? I don't. People would. For you, Elisa, what do you like it? Over noodles or rice?
Let's do rice.
Okay. Fried rice or normal?
I've never had curry on fried rice, but let's do fried rice.
Okay, so we're going to mix it up here a little bit. So we're going to do some fried rice, right? So we go over her house. She has some fried rice that she got from somewhere else like a week ago she went out to a restaurant. And so she's going to put it over the curry over the top of that. And so she takes the curry. She gives a little bit to Garrison, gives a little bit to Melissa. She's like, Kelly, okay, you get some. She gives some to everybody. Blaze gets some. And all of a sudden she gets the very last. It's me, and she's scraping it out, and she barely scrapes out enough for a little bit, and in the bottom of the pan, there's something left. What do we call that, Elisa? What's that stuff left over? Is there a name for that?
The residual?
Residual stuff, right? And so imagine if we were to take out all the stuff that actually creates a pattern. If we were to have data And it creates a pattern of a slope. And we're going to take out everything that creates a pattern, right? And then we have other stuff out here. Hopefully, the residue, the residuals, the stuff that's left over doesn't have a pattern in it as well. Because if it does have a pattern in it as well, that means that something else is taking place as well. And so there could be a few things taking place at one time. So we want to be careful and make sure that that residual stuff doesn't have a pattern in it. It doesn't have a curvilinear pattern in it. It doesn't have a pattern that shows that certain things are taking place in it. And so we want to make sure that we're okay there. Okay? And so that's what we're looking at. Okay? So this is some of our residuals. And so here, when we look at that, like I don't see a smile or a frown, and I'm going to show you a way to look at this and to examine it to what we can do, but I'll tell you what. Remember as a kid driving in my parents' car out on a long drive, and you look up in the clouds, it's like, oh my God. My sister's like, there's an angel. I'm like, no, I actually see a Big Mac because I'm hungry. My other brother and sister, they see something else, and we're all driving, we all see something else in this. So sometimes you see what you want to see. And you can actually imagine that there's a pattern in there. But we're gonna have a technique that I'm gonna show you when we actually run it, to where it will look at it and it'll take away your own personal perceptions. It'll take away some where you're hoping that there's something there, so you actually see it there where it's not. So I'll have a technique for us. But right here, I would say that there's no apparent smile or frown. It does look like there's some type of thing in there, but I don't see a smile or a frown. Okay. Again, I'm hungry, so I see a Big Mac. But that's just me. So we can use also the Durbin-Watson. And so when we have data that's collected over time, we want to detect those autocorrelation. So what we're looking at is, so correlation, things that actually go together. And so you're looking at, what we're trying to find out is there patterns of things that are going together over time. And if there are some type of patterns, then perhaps we have some type of dependency there, right? And so what we want to do is to see if things are, if there's some type of dependency there in our data. So here's where it becomes weird. And I just want to say it because those of you that think deeply, you're going to go, oh my God, wait a minute. Let's do this, right? And this is what's going to kind of blow you away, right? We're looking at dependency. And you're going to say, well, wait a minute. This is independent, this is dependent. And so dependent variable. And if we have a dependent variable, how come you're trying to test if you have dependency? There is a dependent variable there. This is weird. You're saying this is a dependent variable there, but now you're also looking at dependency. This is not making sense. Well, what I want to say is this, that there's always a certain level of dependency that takes place within things. But what we want to do is to make sure it's not too dependent. And that level is actually hard to define. But remember we had that experiment with my brother. He had a car. We had 4 different brakes. And we got the car up to 50 miles an hour, held it and stopped. And we figured out that we figured out, hey, wait a minute, they're all different lengths. And we're like, we can't test it like this because they're dependent. And we were looking at, well, wait a minute, how come the numbers are different? They should all be the same. And the reason why they're different is because we have error here, right? And our error is either systematic or random error. And so there's a problem here, right? And there's a problem because there's a dependency here, right? We should be independently checking these breaks. But there's some things we want to be dependent, right? There's some things we want to be the same. We want to, one, use the same car for all of them. You don't use a minivan for one, a Porsche for another one, you know, no. A Yugo for another, no. We want to use the same car. We want to use the same track, the same driver, the same road conditions, not one in snow, one in rain, and one in a perfect sunny day. No. We want to make sure that certain things are the same, but other things are independent. And so where is that level? And so what we need to do is to make sure that there's not certain patterns, although we're using the same car, we're using the same driver, we're using the same whatever, we want to make sure that there's not other patterns of other stuff taking place in the back that we may not be seeing, right? Who knows what those other patterns could be, right? Who knows what those other patterns could be? And so we just want to make sure that there's not other patterns taking place. Like perhaps there's a certain wind that takes place at 3 o'clock, and we're testing the other one always at 3 o'clock because it's number 3. We test one at 1 o'clock, the other one at 2 o'clock, the other one at 3, and at 3 o'clock there's some type of wind that's taking place and it's blowing against it, so it's making the braking better or something. We just want to make sure that there's nothing else taking place here. So when I say like independent or dependent, we want to make sure that there's no other patterns taking place within here that would create some issue. Okay, so what we're trying to do, again, is to make sure that it's not dependent, but there's a level of it. And that's why when we're looking at this autocorrelation, it has to be above 1.3. You're like, well, why wouldn't it be at 0 that there's nothing here that overlaps? Well, it has to be past a certain level, right? And so if it's below 1.3, it's telling us that it is dependent. Above 1.3, it's independent. It's not perfect, but it doesn't mess with our calculations, and that's what's important to us, as long as the calculations are good, okay? So we're looking at our Durbin-Watson, and with our Durbin-Watson, this is how we calculate it out. And are we going to calculate it out by hand? No. It's going to be calculated for us. And we're looking at for our autocorrelation, right? And so what we need is above 1.3, right? It has to be above 1.3. Okay? So autocorrelation, we're looking at this. If we see here we have a snake-like pattern, and there could be a problem there, right? What we don't want to see is some type of snake-like pattern. But our Durbin-Watson has to be above 1.3. Right here, it's below 1.3. What does that tell me? That tells me that my standard error is no good. That tells me our standard error is no good. Is our standard error important? We'll look at that when we go over this stuff later on. Okay. Now we're going to get out of that one, and we are going to go to our next one, our 15. Go through a couple slides there, and we're actually going to run some stuff and see if we can make sense of it. Okay. So in this chapter, we're going to look at how to evaluate the assumptions again. So we're going to go a little bit deeper into them, and if they're violated, what we do, right? And so when we're looking at regression, we're looking at betas. We're looking at slopes. We're looking at intercepts. We're looking at slopes. From those slopes, we can actually forecast what's going to take place in the future. We can see how accurate it is. does that standard error hold, right? What are the numbers going to be? How much money are we going to make? What are our costs going to be? And based off of that, we can make type of predictions. After we make predictions, we want to make sure that our predictions are accurate, because it's not just enough to make them. So we have our assumptions again: linearity, independence, normality, equal variances. And we're going to look at something called our residuals. So the residual is the difference between the observed predicted value and the error for the prediction. So what we're looking at is the error, the stuff that is not part of our prediction. And what we don't want to see is we don't want to see error. We don't want to see issues in that. If we see patterns in there, we have a problem. One of the patterns that we could see is a smile or a frown. That means it's not linear. Another one that we can see is a problem, again, with our independence, and we'd see either a snake-like pattern or the Durbin-Watson would not be above 1.3. For normality, again, we're looking at either a normal probability plot or skewness and kurtosis. And that would allow us to see if our p-values are okay. And the last thing we want to look at is we want to make sure that our data varies equally over time. Okay? And I know that it looks like we just did the same thing again. They say that if you say something one time, people get about 25%. If you say it 2 times, it goes up to somewhere around 60 or 70%. 3 times, even more than that. That's why parents repeat themselves. Kids still don't get it. It's okay. So measuring autocorrelation, we can do that with the Durbin-Watson, right? Autocorrelation. So serial correlation or patterns in the data. Okay. So I think we beat this one up enough. Let's now, what I want to do is to stop this, and let's now go to some data and run this and see what this regression actually does. Okay? I want to actually run this, write it up, interpret it, and understand what is it here that we're actually doing and why is this important? Not just, okay, I see this, I see that, all these things that we're kind of looking at. So let's now, I'm going to grab some data and I'm going to first set up a situation and show you where we're at and show you how we use this. This is a real case scenario. There's a company and it's called Ross. Have you ever heard of Ross, Garrison? The company Ross? Mic on?
Yeah, no, nothing on, but yeah, I have.
Okay. What do they sell?
Clothes.
Yeah, they sell like surplus stuff. Like if you go to Macy's and you see some nice shirts, and they have these shirts that they're in, like, you know, maybe one in black and one in brown, one in white, and one of them in like this funky green color. The black one's a sellout, the brown one's a sellout, the white one's a sellout, the funky green color one is going to Ross, right? And because it's a new brand, like Polo or whatever it is, Ross will take it because somebody will be like, look, I have this type of shirt. It's a Monsolar or whatever it is. People will be like, yeah, it's lime green. But yeah, it's Monsolar. Right? So they like that brand stuff. So it finds its way to a company called Ross. Now, Ross, let me kind of set this up a little bit. Looking at the big picture, Ross sells its clothes to probably people that are anywhere from maybe 15, 16 to maybe.
Lord.
They do have a lot of people that try to buy really trendy clothes and stuff like that, and they're not going to go to Ross, right? Ross is for the people that want to get that brand name, they want to get a little bit cheaper, but it's like not everybody else's first choice, But make no mistake, it's probably a good quality piece of clothing, but just, it's the end part of it, the ones that didn't sell. And so when we're looking at Ross, and we're looking at different age groups and stuff like this, and we find out that even though here at the university, probably the average age of a kid is probably like 20, 21, the average age of people in the United States is, I think, 34 years old, 35, 34, 36, or whatever, depends on where you look at it. They haven't done the latest census is not complete yet, so the data's not out, but I'm going to say 34. The average standard deviation is about, I'm going to do 35, is about 5 years. So one standard deviation is 40, 45, 50, 30, 25, 20. Just to say that, right? And so when you're looking at who Ross is going to look for, and they start doing their demographic studies, they're not going to have, when they're looking at age, it's not going to be a bell-shaped curve. They want their data to be skewed that way, because that's their population. Either that, or they want their data to be peaked or something. Right here, they want the population to be anywhere between probably 25 and 45. So they want their data probably peaked, and they probably want it in here. They're not looking for people out here, or they want their data skewed to one side, but they don't want their data normal now. So what they're going to do is they're going to go out and they're going to look for a population. They're going to look for a city that has people between, or a high concentration of people between these ages. They may be even looking for people that have incomes between certain incomes. The people that are making over $300,000 a year, they're tightwads, so they'll be shopping at Ross. The people that are making $50,000 and under, they're going to be shopping at Macy's. I don't know why that works like that, but it does. So they're probably going to want to look at certain populations, and sometimes it's different than what you'd imagine, that they think would shop at their stores. And so once they've established that, so Ross actually hired me to forecast how much money they would make if they opened up a store in the North Shore. So first what we did was we wanted to match to see if the demographics of the age and the income were of what the people that normally shop in their area. So then what we're trying to do is we're trying to see, based off of the size of the store, could they make a profit? Would they be able to make money? We're trying to forecast how much money Ross would make in the North Shore. So what we did was we found out that the size of the store was already built. And what they were going to do is just to put, so a store, for the most part, I don't care if it's Costco, Walmart, Target, whatever, 4 walls. They take 4 walls, they put some type of floor down. They put not even decoration on the walls, to be honest. They put shelves in there. I don't care if it's Costco, Walmart, a bar, a restaurant, whatever. But if it's a store, they just put like, however they design their shelf systems. They put shelves in there, escalator, bathrooms. They paint the walls a certain color, and maybe they put up some stickers on the wall. But that's a store. That could be Target, Walmart, Costco, whatever. There's not much of a difference between how it's made them an entrance and exit and shelves. So what Ross wanted to know is, based off of the size of store, the location, when you sell products, it's all about how much shelf space you have. Because based off of how much shelf space you have, you can put products there, and then we can see what's the average turnaround time of those products in certain areas like that. And based off of that, that will tell you how much money you can make. It's almost like a fisherman. If you put in 5 hooks, you have a higher probability of getting something than 1 hook. And so what they're looking at is shelf space. And so with the location over in the North Shore, and it's already built, they were just going to build out the inside of how they're going to put their shelves and the floors or whatever they do in Ross, right? They're trying to figure out, okay, how much shelf space could we have in this Ross? The interesting thing is when we look at shelf space, there's a couple things that come into play. One of them is called the ADA rules. And so the ADA rules tells you how far the shelves have to be separated from each other, right? Also fire marshal rules, because if a fire breaks out, they have to have so much of a fire break so the fire person can get in there with the fire hose and put it out. Also, so the sprinkler system has enough space in between the things to where it can fully do whatever it has to do. But ADA also has that 2 wheelchairs have to be able to pass, right? And also with the shelves, if it's not like a distribution center, it's not a warehouse or something like Costco or whatever, that the shelves can only go up a certain height because either people that are shorter or people that are in a wheelchair can't reach the stuff up there. So it can only be a certain height too as well. So here in Ross, we found out that they would be able to have about 50,000 square feet of shelf space. That's it, 50,000 square feet. Now, the bottom line of how much it would cost in fixed cost, rent, how many employees they forecasted out, right? Insurance, electricity, water, gas, trash, all the rest of that stuff. They needed to make about $500,000 a month, right, to gross. Now, could they make it with 50,000 square feet? Do you launch this place or not? Let's take a look at that. Let's take a look at the data, right? Real project, real life thing. Let's see if we can actually open up a Ross based off of the data that we have. So, Moana, if you can see this screen, give me a thumbs up. Moana? Okay, there we go. All right. So here we have, these are 18 different Rosses, and these are the different amount of shelf space they have in thousands of feet. And this is how much revenue they make in thousands of dollars, right? And so based off of that, we want to see how much, what's the average amount of money that Ross makes per square foot of shelf space. And then we can estimate how much money we're going to make. But we need to make sure that everything's constant, right? Because we don't want to be off on these numbers. So now let's run our regression and see if we can make sense of this. So I'm going to run my regression, simple linear regression. So we have 2 variables. We have a dependent and an independent. Our dependent variable is our y variable. Our dependent is our y variable. The x is independent. So I'm going to run all this stuff. So I don't know if you guys noticed, but we're now back up and running with our videos. So I posted yesterday's video and the video from the day before. Now I'm going to go back and post the ones prior to that as well. So now we're back up and running. We're going to get all those things hopefully done by the end of the day. By the end of the day, we should also have all of our midterm scores posted. And by the end of tomorrow, we should have all of our problem set up to 3 graded. I did launch problem set 4, and we're going to start working on that hopefully in class tomorrow. Okay. So here we're looking at our shelf space for Ross. What this multiple R tells us, this is our correlation. That's how strongly related shelf space is with revenue. Do we see that? 99%. This R squared tells us how much of our revenue can be determined, how much does the increase in shelf space increase our revenue? 99%. That's what it's telling us. Every time we increase our shelf space, 99% of that increase will increase our revenue. 1% doesn't, for whatever reason, right? So this is telling us the percentage of increase in shelf space increases our revenue. Okay, that's what that tells us. We'll get to adjusted R-square later. Our standard error tells us once we forecast how much money we'll make per square foot, this tells us how much money, how much our predictions will be off by. This is governed by the Durbin-Watson. What do I mean governed by? If the Durbin-Watson's not above 1.3, that number is no good. If a Durbin-Watson's not above 1.3, that number is no good. This is the amount of observations we have. This right here is an ANOVA. That's our degree of freedoms. Why? Because we have two things we're looking at, shelf space and revenue. A degree of freedom is the amount of variables we have minus 1. That's our sum of squares. Again, if you go back to that, when we calculated out our standard deviation and look at sum of squares, that's what it is. Our mean of squares is that number divided by that number, which is that number. That right there tells us if we actually have a linear regression model. Do we actually have a linear regression model? So we like to write hypothesis. And does V1 equal 0, which means that there's no slope, or does V1 not equal 0? Okay, and so we use that to reject our null or not. If we reject our null, then that means that it doesn't equal 0. If it equals 0, that means that there's no slope. V1, again, is our slope. Okay? What this is telling us right here, looking at our coefficients, that 11.22, that tells us how much revenue, either how much revenue or cost, what that's telling us, doesn't matter what that is, I mean, because right now we're looking at revenue, but if we're looking at cost, it would tell us how much cost. That's telling us right now what we would have, what we would make, right, if shelf space was at 0. What's our intercept, right? If everything was at 0, where would we be at? That's what that's telling us right here, okay? You with me so far? So it's telling us if we had 0 feet of shelf space, if this is in $1,000, we'd make $11,000. Give or take $13,000. Right? This tells me if it's a slope, but it doesn't have to be a slope because it's an intercept. And this tells me 95% of the time, we would make anywhere from, we would lose anywhere from $18,000 and make anywhere up to $40,000, but that number's right in the middle. Now, if I take that number, and if I use this as a standard deviation, I double that, add that to that, I get that number. If I take this number, multiply it times 2, 2 standard deviations from the mean is our 95% confidence interval, subtract it from that number, I get that. So just how we do our standard deviations is that. So this right here tells me for every foot of, this should be shelf space, not revenue, but for every foot of shelf space I have, our profit goes up by roughly, right there is like, if it's in hundreds of dollars, it would be like in $9. So that's how much our shelf space, our revenue would go up per foot of shelf space, right? And so now, give or take that amount. That's our T-stat. So now we can start to figure out, well, how much money would we make? And the way that that looks and the way that we figure that out, and this is our formula. So Y is our revenue plus our intercept plus B1 times how many feet we actually have of shell space plus or minus $11,000. So now all we have to do is plug our numbers in there and kind of figure that out. So again, Y is intercept Y is revenue B0 is our intercept. If all other variables are at 0. Our B1 is our square feet. So it's our feet of shell space of revenue per square foot. How much money do we make per square foot? And our standard error is how much we will be off by. Okay. So now let's see if we can figure this out. What the heck does this mean? Now we're going to solve this case. We're going to solve this business case, right? $9 per square feet. 11. 100. We do hundreds. 1100. $9.24. Okay. Let's solve this and see where we're at. Do we open up Ross? Do we open up the Ross over there? So Y equals B0 plus B1 times X1 plus or minus 11. What we're implying is that the more square feet we have of shell space, the more revenue we'll make. Okay? Now that slope is equal to $9.24. $9.24. And that, but our data stops right there, but what we do is we actually make an intercept. So at 0 square feet, our intercept is $1,100. So we'll make $1,100 with 0 square feet. That is B0, that is B1. So B1 is a slope, B stands for beta. B stands for beta. When you get in your finance classes, your professors are going to be talking about betas. They're going to be talking about mutual funds and all kinds of investment packages. And they're like, where's the beta at? So what they're looking at is a moving average, okay? A moving average, a slope, okay? And that's what we're talking about with betas, moving averages and slopes. And once you get into finance class, you're going to talk about beta, 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 beta. This is what they're talking about, okay? That is beta 0, 1100. Beta 1 is $9.24. So let's just plug them in. $1,100 plus $9.24 times 50,000 plus or minus $11,000. This is going to tell us how much money we're going to make. Do we open up this store? Can you do me a favor, Moana? Do you have a cell phone with a smartphone or whatever? Calculator? Okay. Can you multiply $9.24 times 50,000? What is that?
What is it again? $9?
$9.24, so 9.24 times 50,000.
It's 462,000.
So 462,000 plus $1,100 plus or minus $11,000. So can you do me a favor? What's 462,000 plus $1,100? Hannah Banana, what is, you might be saying that right. Okay.
What is it? 1,100?
So what's 462,000 plus $1,100?
473,000.
473,000. That's 1,100. That's 462,000. Okay, let's do it. 473,000. We'll just put it at that. We'll round it off. Okay. You with me here, though? So, see this number right here? With that amount of shelf space, we should make 473,000. But this number, remember how we had somebody that was jumping, and the average distance they jumped was 6 feet, but nobody really ever jumped 6 feet? It was off by roughly 2 feet. And so we say our standard deviation, like, yeah, it's 6 feet, but just that number's going to be off by 2 feet. Do we see this? What we're saying now is we're going to make 473,000, but it's going to be off by 11,000. Either below that number or above that number, but that's kind of where we're going to be at. So we need to make that. Lauren, do we open up Ross?
No.
No. No, not at all. There's no way. Like, are you sure, Lauren? I mean, how do you know that your numbers are accurate? You're like, well, how about this number? Could it be more or less? I mean, is that number okay? Is it accurate? You're like, well, let me check. How do you check the standard error? Durbin-Watson. Oh, wait a minute. Our Durbin-Watson is greater than 1.3? Yep, that number's accurate. It's going to be off by 11,000. Oh, okay. How do you know that slope is real, that slope's not, that slope is actually constant like that? I mean, could that slope be wrong? Could it be more than that? Okay, well, let me check the slope. So you know what I'm going to check? Linearity. I want to make sure it's not curvilinear. Nope. I see randomness. Slope's okay, man. That's okay. No, that number's okay. Well, how about, are you sure that it's really, that this thing really works, that the linear regression is really okay? So we write our hypothesis. B1 equals 0. B1 does not equal 0. What that is literally saying is if B1 equals 0, then we really don't have a slope. As shelf space increases, revenue doesn't increase. If B1 doesn't equal 0, that means we have a slope. And so we look at our p-value, and because our p-value is extremely low, forget what it was, but it's extremely low, way below 0, and our level of significance is 0.5, we can reject that. We're almost 100% confident that there's a slope. And then they say, hey, Lauren, are you sure about that p-value? Oh, let me check my skewness or kurtosis. we're going to take a look at those right now to validate this model. But at this point right now, no, Ross ain't happening, right? They ask you, should I open it up? You go in as a consultant, should I open it up? Like, no. Well, then people that want it to open up because they're like, hey, I was planning on moving to Hawaii, right? I wanted to be the manager. Maybe Sarah's not right. Maybe her numbers are wrong, right? Because they're just hoping, they're dreaming, they're, you know. Sarah's like, no, man, I looked over those numbers. It's not going to work. And they're like, well, can't we do this? No. Natalie, can you give me a thumbs up if you can see this screen? Okay. So now let's make sure that our numbers in this are actually accurate, that our test is accurate. Let's take a look at this. So we want to check our linearity. Does anybody see a smile or frown in there? What do you think, Carson? Smile or frown?
Sorry, I couldn't hear you. What'd you say?
Do you see a smile or a frown pattern in there?
Yeah, I see a smile, kind of like right in the, yeah, from like 5,000 to 8,000.
Okay. Now, other people would say, okay, if that was missing, I wouldn't see anything in there, or if that was missing. Or maybe one way to check to make sure that we're not reading into things is you go right here on the number, on one of those dots right here in the center somewhere, and right click on that. And you see this right here, and you're going to want to add a trend line. Sorry, let's do that again. Let me undo that. I'm going to go over here, right click. And as I add the trend line, I'm going to change it to a polynomial. So I'm going to put a smile or a frown in here. I'm putting one in there. That doesn't occur by itself. And now what I want to do is I want to measure to see how close these data points are related with that. So I'm going to put in R squared, because R squared tells us how much one of them is related with another one. So if we have an R squared that's above 0.2, 20%. If 20% of these data points are aligned with it, then we have that pattern. But if we notice our R square here, it's 1.1, so it's not quite to that number. So what I would say, no pattern. I know we see that, but all the data points don't really align with it enough. So I would say, no, they're not there. There's nothing there. So I would say for linearity, we're okay. Okay, linearity is okay. Independence. See our Durbin-Watson? Above 1.3. That tells me that our standard error is okay. That number 11 that we had in our formula, our standard error is okay. How about for normality? For a normality, what we want to do is we want to look at our residuals. And see these? I am going to run my skewness and kurtosis based off of that. We've got descriptive statistics. And I'm going to see, based off of the residuals, what they look like. That tells me my p-value is accurate. Okay. Now, the last thing I want to check is my equivariances. And what I'm going to do to make that is I'm going to plot my predicted against residuals. Insert, scatter diagram. And what I don't want to see is a wedge shape. And so I would say that my assumptions are correct. Now the last thing I want to look at here is my, can I reject the null? Is this model even good? And so my significant F is my p-value. So what this tells me right here is I'm going to move that decimal place 17 places. So it's an extremely low p-value, so I can reject my null. Let's put this in a, and you're looking at this, oh my God, there's so much stuff to this. How do I write this up? Okay, hang on just a second. And let's make sense of this. Because right now, if I were you, I'd be confused, like all this stuff that I'm putting, how does it all fit together? I get it. Okay. Let's write this up. Let's see if we can make sense of this. I'm getting ready to, I'm launching or trying to launch our hypothesis write-up doc. So those of you that have that, if you go to your hypothesis write-up doc, it's in your, the same one I said to use for ANOVA, t-test, z-test. She's launching right now. Should be done in just a second. Meanwhile, does anyone have any questions while this thing is loading? Where are we at, Sarah?
I can see the screen. There's the residual plot.
Okay. We're going to launch the hypothesis write-up doc. It should be, do we see that? Somebody give me a yes. Lauren? Okay, good. So let's take a look at this. We're not going to look at the ANOVA, the z-test, the t-test. We're going to look at regression. So all the rest, I'm going to delete. Okay, so here's our regression. So let's write this up and make sense of it. What is it that we're trying to figure out here? So with our regression, what I'm going to write is B1 equals 0. What does that mean? B1 equals 0 means that, ouch. B1 equals 0 means that when we increase shelf space, our revenue doesn't increase, that there's no slope. So right here, I'm going to write B1 does not equal 0. Okay. So it was hypothesized that increasing shelf space would not affect or would not increase revenue. Okay. There is significant evidence to reject the null hypothesis. The significant F, I think it was 17 zeros and then a 1. I'm going to just write 0, which is below the level of significance at 0.05. I'm just going to write 100% confident that one of the slopes is not equal to 0. For our model, it wasn't 76% of the increase or decrease. It was actually like, was it 97 or 98%? That would be our R-square. I think it was 98%. 98% of the increase or decrease in shelf space is attributed to increase in revenue. Okay. We're not going to do adjusted R-square, because we don't need that yet. We will on the next model. The slopes for the independent variables indicate if you had no shelf space, you would earn $1,100. And for every foot of shelf space, you would earn $9.24. With me? So that's our prediction right here. To validate this model, I will check the assumptions: linearity, independence, normality, equal variances. The assumption of linearity is valid. There was no patterns of parabolas, smiles, or frowns. To validate independence, I checked the Durbin-Watson. It elicited a number above 1.3. So we're good, right? So 1, it's linear. 2, our standard error is okay. To verify the assumption of normality, I checked skewness and kurtosis. The skewness and kurtosis were both within normal range. To validate, and so that tells me my p-value is okay. I checked, to validate equal variability, I checked the residuals plotted against predicted data. There was no wedge-shaped pattern indicating the data is equally variable. The overall error of the model, standard error, was, I think it was 11,000. The independent variables, the independent variable, well, we don't need to check this because we're not, we'll do that on the next model. That right there, my friends, for the most part, is multiple regression right up. All the stuff that we looked at, all the different like Durbin-Watson, the shape of the data, residuals, and all the rest of this stuff can all be boiled down into just that. And that's how we would interpret it. It was hypothesized that increasing shelf space would not increase revenue. There's significant evidence to reject the null hypothesis. The significant F was at 0, which is below the level of significance of 0.5. I am 100% confident that one of the slopes is not equal to 0. 98% of the increase or decrease in shelf space is attributed to the increase of revenue. The slopes for the independent variables indicate if you had 0 feet of shelf space, you would earn $1,100. For every foot of shelf space, you would earn $9.24. To validate this model, I checked the assumptions: linearity, independence, normality, and equal variances. The assumption of linearity was valid. There was no patterns of parabolas, smiles, or frowns. To validate independence in the model, I checked the Durbin-Watson. It elicited a number above 1.3. The assumption of independence is met. To validate the assumption of normality, I checked the skewness and kurtosis. Both were within normal range. My p-value is accurate. To validate equal variability over time, I checked the residual plots predicted against against predicted, there was no wedge-shaped patterns, indicating that the data was equally variable. The overall error in the model was $11,000, right? That's it. Let's go back to our regression and take a look at it again, because I want to make sure that we're kind of looking at this and able to put what we just wrote up back to our numbers. How many of you guys would like to have a tool for this? How many of you guys would like to have something that you can read that would actually like plot all this stuff together, that would explain what all this is? I see a smile there from Lauren. Is that a yes? Okay. Let me do this. Give me a thumbs up if you can see this, Wilfred. Do we see my Lalima page? I'm going to go to Excel note files. I'm going to go to chapter 13. I'm not going to go to that. Go to the next one. Second one or the third one? Okay, exit that one. Third one. Can you guys see the Excel or no? Give me a no. Somebody give me a thumbs down. Give me a thumbs down, Natalie, if you can't see it. Okay. So let me stop sharing and let me go back. Let me go to this one. All right, Natalie. Cool. Remember on the first day of class? The very first day, I know it seems like a long time ago, I showed you guys this slide. And I said, watch, you're going to be able to read this. And you thought, no way, this is crazy. And so now let's take a look at this. This is our regression. Multiple R, correlation. R square tells us how much of the increase or decrease in one is all of them. It shows us every single thing in here, what these plots mean, all of it, all of it. Okay, so if you want to understand what all these mean, it shows you. So that tool that you asked for, Lauren, where you're like, oh yeah, that would be nice. Guess what? I put it there before the class started because I knew already, because I read, right? I looked at my horoscope and it says, in 6 weeks, Lauren is going to ask for some type of plot. And I thought, no way, what's the probability of this? Turns out it was right. So I put it up there just for you. And all the rest of you too. Just kidding, right? I've done this for a little bit, so I kind of know. So we have this tool here for you guys. So what I want to do now is I need to get a heads up. I need to find out where it is